Next, we have the uniform solid cylinder, which we are figuring out the moment of inertia around the cylindrical axis. So we have the solid, I'll put uniform, solid cylinder. And we are figuring out the moment of inertia about z, the long cylindrical axis of this. So we are rotating it as such, and we're figuring out the moment of inertia if we were to rotate it like that. Let's define some things. We have our cylinder, which looks like this. The axis that we're rotating it around goes through there. R, big R, I'll write it here. Big R is the radius of the item. We're going to break it into a infinitesimally infinitesimally small pieces, but an infinite number of them, which have a thickness class what? dr, and a radius of what class? Little r. Notice this is where we introduce the concept of little r being the variable, big R being the capital R being the one that does not change. L would be the entire length of the whole thing. And we're trying to figure out the moment of inertia about the z-axis, which is equal to the equation for the moment of inertia. Please, Hamza.
Integral r squared dm.
Integral of r squared dm. So notice there are a lot of similarities between what we just did with the center of mass and what we're doing now with the moment of inertia, because we have the integral of something, r, with respect to mass. So we have the same issue. So we need to deal with the fact that we have this dm and an r. In this particular case, we are going to use r because it is a radius rather than x or y. Therefore, what are we going to do with dm here? Look.
Take P, D, or rho, dV.
Let's just start with rho. What is rho equal to?
Over V.
The mass divided by the volume, right? So let's just start with the basic definition of volumetric mass density. That means it's also equal to dm over dv. This is the easiest place to start. Now we have the fact that dm is equal to rho times dv. Okay. What is the volume of dm? This guy right here is dm. The volume of dm, please. Tyler.
2 pi r L dr.
2 pi r L dr. It is the circumference multiplied by, it's easiest, if you recall, if we look at it in terms of this, the shape, right, of dm. And it's easiest if I take my scissors and I cut it, which is why I collect these, so that we have this is the volume we're trying to figure out, right? So it has a side, 2 pi r, the circumference, multiplied by a side, L, multiplied by the thickness, which is dr. So the volume, dv, is 2 pi r times the length times dr. So we can substitute that in now for the moment of inertia. Let's do that right down here. Moment of inertia about the z-axis then is going to be equal to the integral of r squared times 2 pi r times L times dr. Let's do two things. Let's take out what we can, what are constants, and get the limits, please. Hillary.
2 pi L is...
Yeah?
What happened to
Rho. That is a bummer, isn't it? So we do need to work on that. No, wait. So we've got dv, so dm then is going to be equal to, thank you, 2 pi rho times 2 pi r L dr. So we do need a random rho in there. Rho, okay. So then we have the integral of, what do we have left? R cubed dr, and the limits, Hillary.
From 0 to big R.
0 to big R. Little r varies from 0 to big R. Good. Let's see. At this point, we have 2 pi L rho r, little r to the 4th power divided by 4 varies from 0 to big R. Therefore, we have pi times L times rho times big R to the 4th power divided by 2. Moment of inertia should not be dependent on the length of the object nor the density of the object. Solution. Next. Find rho, okay? Coming back to, we'll do it right here, rho, which is equal to the total mass divided by the volume. So we could have the total volume, so this is equal to the total mass divided by the volume total. What is the total volume here? Go ahead.
Total volume would be pi big R squared L.
Great. So we can substitute in for the moment of inertia about the z-axis. It's going to be equal to pi times L times big R to the 4th power divided by 2. All of that multiplied by the mass divided by pi r big R squared times L. Let's see, we have some things cancel out. Pi cancels out, we lose 2 of our r's, and we lose an L as well. The moment of inertia about the z-axis then is 1/2 mL squared. mR squared.
Yeah.